We are already familiar with the problem of finding the absolute maximum minimum values of a continuous function on a closed interval. Okay, the extreme value theorem guarantees the existence of these values. Let's review the idea by looking at a problem. Find the absolute maximum and minimum values of the function f of x equals x cubed minus 6x squared plus 9x on the closed interval from 0 to 2. Okay, and if you remember the procedure, we take the derivative, the function 3x squared minus 12x plus 9, and we look for all critical numbers, all points in the domain of the function where the derivative is 0 or doesn't exist. It's a polynomial, so it's always going to exist, so it's just a matter of finding all the places where the derivative is 0 here, and we can factor out a 3 times x squared minus 4x plus 3. We could divide by 3 and factor the x squared minus 4x plus 3 to x minus 3 times x minus 1. X squared minus 4x plus 3 equals 0, giving us two critical numbers. Now we make ourselves a chart, x against f of x. It goes from a to b. This is a continuous function, f of x, on the closed interval a to b, from a to b. So we put 0 in here, 2 here, and any critical numbers that happen to fall between 0 and 2. So the only one we're going to use is the 1. We ignore the 3 because it's outside of our interval. Then we evaluate the function. Okay, we go back to the original function and evaluate it at these 3 values. Of course, you can do all of this on your graphing calculator very simply using the table option. If we let x be 0, y would be 0. If x is 1, 10 minus 6 is 4. And if x is 2, we would get 8 plus 1826 minus 24, which is 2. Now, when we substitute into the original function, not into the derivative, once we do this, the largest of these y values is the absolute maximum, and the smallest is the absolute minimum. So the absolute maximum value is 4, occurring when x equals 1, and the absolute minimum value is 0, occurring at x equals 0. If we were to actually graph this function, once again using your graphing calculator, turns out, looks something like this. We have the point 0, 0 on it, 1, 4, 2, 2. And what is not obvious from the work that we've done right over here is that there's another turning point at 3, 0. The function looks something like this. However, if we took the entire real line, this function would not have an absolute max or an absolute min. However, we were only considering it between 0 and 2. Only this region, from here to here. And we understand that between here and here, yes, the absolute maximum value was 4, occurring at x equals 1. The absolute minimum value was 0, occurring at x equals 0. Although this is the entire curve, we were only interested in it between 0 and 2. And we have the absolute max and the absolute min. Now, the title of this videotape is Applied Maximum Minimum Word Problems. Now, this is an absolute maximum problem. You're given a continuous function on a closed interval. In the word problems, we're going to be given a problem, except we're not going to be given the function and the interval explicitly. You're going to have to figure it out from the words of the problem. And the problem is you really want to find absolute max and min. If you're doing a real world problem, and you have a function which represents, say, profit, you don't want just the local max, you want the absolute max. You want to get the greatest possible profit. Okay? Similarly, if you were trying to, say, minimize costs, you want the absolute min, you want the absolute max in a word problem. If you're graphing, if your basic interest is graphing, then you want all the local maxes and mins, all the little hills and valleys of the function. They're very important from the point of view of curve sketching. But in word problems, it's really the absolute max and minimum values of a function on an interval that you're interested in. Now, if it turns out that it's a continuous function on a closed interval, we can handle it by this procedure, assuming we can decipher the problem, figure out the function in the interval. If it's a continuous function on a closed interval, no problem, we'll do it this way. What if now we may have a problem that function may not be continuous, the interval may not be a closed interval? What are we going to do? Well, if it's a continuous function, okay, so we have a continuous function, but the interval may not be closed. There's another approach that we can take. If we have a continuous function, okay, on an interval, not necessarily closed, but it only has one turning point, okay, only one turning point. There's a local min, say, here. Then, if it's the only turning point, I can also proclaim it to be the absolute min. How come? Well, how am I going to get something lower than that? Another loop of the curve, but I said it's a continuous function, so I can't have just another loop here. Turning around and coming down? No, I said one turning point. So if it's a continuous function on an interval, and if there's only one turning point, then if I can prove that it's a local min, then I'll know it's an absolute min as well. Similarly, if there's only one turning point, and it's a continuous function, and it's not a closed interval, but it's a continuous function, and if it's a local max, then it has to be an absolute max as well, for the same reasons, that it has to be continuous and there's only one turning point. Okay? If you have more than one turning point, of course, all bets are off. If you have more than one turning point, then I can't be sure that I have, it may be that I'll have an absolute max, like I do here, but of course this problem has no absolute min. You certainly can't be guaranteed anything. Okay, so let's try the first word problem. The only way you're really going to understand this is to actually practice. Okay, for our first word problem, let's try this. Rectangular area is to be enclosed by 100 feet of fencing. What should be the dimensions of the rectangle if we want to enclose the greatest possible area? Okay, this is basically a problem of trying to maximize an area subject to a fixed perimeter. Let's see if we understand the problem. We have a rectangular region. There are various rectangles that we can make with 100 feet of fencing. We could, for example, it's not exactly drawn to scale, but we could have 5 feet on either end, and then 45 feet on these sides. 45 and 45, 90 and 10, using up 100 feet of fencing. Or we could have 10 feet on either end, and 40 feet on the other sides, 40 and 40, 80 and 20, 100 feet of fencing. As all of these rectangles have 100 feet of fencing, the perimeter is 100 feet, except the area changes. Here the area, length times width, is 400 square feet, which we could write either word square feet or write feet with the power 2, which is read square feet. Here, the area would be 45 times 5, or 225 square feet. So it does matter how we break it up. And what we're looking for is the rectangle that will have the greatest possible area. This is how we know it's a maximum problem, max-min problem. Greatest, synonym for maximum, or the maximum possible area. So we want to maximize the area of the rectangle. Now, obviously, we're not sure what the length and width should be. In general, let us say that the rectangle is going to have dimensions x by y. So the area of the rectangle is going to be x times y. I want to maximize the area of a rectangle. Now, this is not exactly like the problem that we just did. The problem that we just did, we wanted to maximize or minimize a function of x, a function of only one letter, subject to x being constrained on a certain interval. So we have a little bit of work before we'll have it looking like the problem that we just did. Okay, first problem is that, I mean, you can call this a if you want to call this, okay. We have these two letters, x and y. We'd like to get it down to a function of a single variable. How can we do that? There's usually extra information in the words of the problem that will enable you to eliminate one of the letters. And here it's the business of the 100 feet of fencing. What they're really telling you is that the perimeter of this rectangle, which is x plus y plus x plus y, or 2x plus 2y, the perimeter has to be 100 feet. Obviously, if we want to get the biggest possible area, we're going to use the entire 100 feet of fencing. We're not going to leave half of it in the garage. We're going to use the entire 100 feet of fencing. The perimeter of this field is going to be 100 feet. 2x plus 2y should be 100. So, dividing by 2, x plus y will be 50, or y is 50 minus x. Okay, so that's good information to have. We can take this value for y and substitute it in here. We want to maximize a, which is equal to x times y, but now we know y is 50 minus x. Or maximize a, which is 50x minus x squared. If you call this f of x, it would look now like the problem we just had. We want to find the absolute maximum of, say, f of x equal to 50x minus x squared. Now, what we're missing is the interval. Can x be anything at all? Are there restrictions? Well, I think we would all agree that x certainly can't be negative. There's a question whether or not x could be 0. Let's, for the moment, say x could be 0. Or positive. Now, how high can x be? Can x be 200? No. You only have 100 feet of fencing. Can x be 100? No, because if you use up 100 here, you got nothing on the other side. That's no good. So the biggest that x could be would be x has to be someplace between 0 and 50. Now, there is a question about whether there should be an open interval or a closed interval. We'll discuss it both ways. We do the problem two different ways. If you think it's a closed interval, you're saying that I will accept the fact that x is 0. If x is 0, that means I'm going to have a dimension 0 on this side. The entire 100 feet is going to be used here, so it's 50 by 0. This is 50, that's 0. The area is 0. I mean, it's an area. You may not like it, but it's an area. On the other hand, if x is actually 50, that's 50 here, 50 there, nothing left for the other two sides. Once again, the area is 0. Whereas if x is either 0 or 50, obviously the area is going to be 0. Okay, let's try to do this. Basically, it's to maximize a, which is 50x minus x squared, on the interval from 0 to 50. Now it looks, if you call this f of x, it looks just like the problem we just did. And of course, we would take our derivative, 50 minus 2x, set it equal to 0, get our critical number. In this case, there's only one critical number. 2x is equal to 50, x equals 25. And our procedure would be to make the same kind of chart we made before, x, and here would be a instead of f of x. We'd go from 0 to 50 with any critical numbers that happen to fall in between. X equals 25 would go right in here. And we figure out what a is in each of these cases. Of course, we already know if x is 0, a is 0. If x is 50, a would be 50 times 50 minus 50 squared would also be 0. If x is 25, if you remember that this had come from the line before this was x times 50 minus x. If it was 25, it would be 25 times 25. Or 625 square feet. And the largest of these values is the absolute maximum. And of course, the absolute maximum value for the area, the greatest possible area, is 625 square feet when x is 25. And of course, when x is 25, since y was 50 minus x, y was 25. And the optimal way to do this was a square. 25 feet on each side. The area came out to be 625. Notice the other answers that we got, 225, 400. Okay, we're getting larger in this direction, approaching the square, which was the optimal solution here. Now, suppose you say, I'm sorry, I have difficulty with this closed interval. As far as I'm concerned, the problem is to maximize a equal to 50x minus x squared on the interval from 0 to 50. In other words, I do not accept that it's a closed interval. I really feel it's an open interval. Okay, we can still do it. You start off the same way. You get the critical number. In this case, just 2x equals 50, x is 25. But what you try to do is to show, I'm going to take the approach, there's only one turning point, continuous function on this interval, not closed, but okay. If I can show that this one turning point is a local max, the fact this one turning point, this continuous function, has to be also an absolute max. So that's another way to get it. In this case, I would make a chart, x against a prime. Put the 25 in, take a value less than 25, let's say 20, a value more than 25, let's say 30. Figure out what a, not a, but a prime is in this case. 50 minus 2 times 20, 50 minus 40 would be positive. Plugging in the 30, 50 minus 60 would be negative. If the derivative was positive, the function would be increasing. If the derivative is negative, the function was decreasing. Since the function was increasing before the critical number, decreasing after, increasing then decreasing, there must be a local max at 25. Okay, but local max, and there's only one turning point. This implies it must be also the absolute max. So you can get the information also even if it's an open interval. Okay, so either you consider this a continuous function on a closed interval or a continuous function on an open interval. In this case, you actually do it the way we handle continuous functions on closed intervals. Here we find, and we get the absolute max directly. Here we get the local max, but the fact that there was only one turning point on the interval gives us the fact that it's an absolute max. So it can be done either way. Now, I'd like to consider a related problem. This problem, we had a fixed perimeter, and we wanted to maximize the area. Now, a very related problem is the problem that I've written up here. Find the dimensions of the rectangle with the smallest perimeter, which has an area of 900 square feet. In the last example, our perimeter was fixed, and we wanted to maximize the area. We had a certain amount of fencing. What's the biggest rectangle we can make? Here it's a different story. Here we need a certain area. Maybe you want to plant something that requires 900 square feet. We want to figure out the smallest perimeter. In other words, fencing costs money. I need 900 square feet, but I'd like to fence it in such a way that's the most economical, have the smallest perimeter, because the smallest perimeter, smallest amount of fencing. Okay. So let's see what we can do here. Smallest perimeter tells me that this is a minimum problem, minimization problem. We want to minimize the perimeter of a rectangle. Okay. The perimeter is 2x plus 2y. And we face the same problem that we had before. Whatever we want to maximize or minimize, I'd like to get as a function of only one letter. I have two letters. Okay? But we can handle this by the extra condition that says the area of this rectangle must be 900 square feet. The area is length times width. The area, length times width, is 900, from which we can get that y is 900 over x. So we would be able to write this as a function of one and only one letter, namely to minimize perimeter, which is equal to 2x plus 2y, but y is 900 over x. As was p was 2x plus 2y, but y was 900 over x. So we want to minimize p, 2x plus 1800 over x, subject to x being restricted to some interval. Now here we don't have the options that we had the last time. The last time you could have thought of it as either a closed interval or an open interval. Here you don't have that option. Clearly, x cannot be 0. You can't have an equal sign there. If x is 0, first of all, you'd have division by 0 here. Obviously, the area cannot be 900. So neither dimension can be 0. The area is going to be 900. So x cannot be 0. As far as an upper bound, there actually isn't any. There's no limit to how much fencing you could waste if you wanted to. In other words, you could have this 1 foot by 900 feet. You'd have the area of 900 square feet. You could have it 1/10 of a foot by 9,000 feet, and so on. So if you want to waste fencing, you can have this going millions of feet in this direction and very, very small amount in that direction. So if you want to waste fencing, sky's the limit. So x can really be anything between 0 and infinity. There's certain practical limitations how big you can make it, but from the point of view here, it's certainly not a closed interval. We hope there's going to be only one turning point on this interval, and then we could use the idea that a local max would be an absolute max, or in this case a local min would be an absolute min. But as far as closed interval, that's out of the question. Okay, so let's see what we can do. I want to get the derivative, so let me rewrite this as 2x plus 1800 x to the minus 1. You could use the quotient rule. I find this a little easier. I take the derivative. Derivative of 2x with respect to x is 2 minus 1800 x to the minus 2, or 2 minus 1800 over x squared. X to the minus 2, the x goes down to the second power. The 1800 stays up. And I can set this equal to 0. 2 would be equal to 1800 over x squared, cross multiplying. 2x squared is 1800. X squared is 900. X would be plus or minus the square root of 900, or plus or minus 30. Now, looks like there are two critical numbers. However, the deal is this. This is the interval. X equals 30 is the only critical number on the interval. So even though there are two critical numbers, only one of them applies. Obviously, we don't have a dimension of negative 30 feet for a rectangle, but this is our interval. And x equals 30 is the only critical number on that interval. So if we could show it's a local min, we would have the absolute min. Now how would we show that? We'd make a chart x against p prime. We'd take our critical number of 30, try a value less and a value more. Anything that, is convenient. You could try 10. You could try 40. If you substitute in 10 into p prime, this is a nice form for p prime to use. 2 minus 1800 over 100. 2 minus 18, it's certainly negative. If you substitute in 400, 2 minus 1800 over 1600, okay? 1800 over 1600 is, 2 would be 1200 over 600, minus 1800 over 600 is certainly, 2 would be 20, okay, sorry. 2, if you substitute in 40, you get 2 minus 1800 over 1600. Okay, so 3200 over 1600 minus 1800 over 1600, it's positive. The function was decreasing, then increasing, so you have a local min and only one turning point, which implies that you have found the absolute min. So what is the question? The dimensions. Okay, you should always answer the question. X equals 30 is going to be one of the dimensions. If x equals 30, y will be 900 over x, 900 over 30. Y will also be 30. So we have x equals 30, y is equal to 30. And once again, the final answer is going to be a square. So it would appear that not only is the square the way to maximize area for a fixed perimeter, it's also the way to minimize perimeter for a fixed area. Okay, in other words, all things being equal, a square is a very optimal way to do things. But what we're going to do in the problems that follow is to sort of make little changes in the problem so that the square will no longer be the answer. We'll have to work out the answer. So let's go on now to problem 3. In this problem, number 3, we have the following. It is desired to fence off a rectangular field, 3,200 square yards in area, along the straight bank of a river. No fence is needed along the river bank. What dimension should the field have if the amount of fencing used is to be a minimum? So we have our river here. And we're going to fence in this field. Maybe we're going to keep animals or something in this field, this enclosed region, but we don't need the fence on the riverside. That's a natural boundary. So we just need the fence in the other 3 sides. So let's say x, x, y. Now, here it says the word minimum directly, so we know it's going to be a minimization problem. We want to minimize the amount of fencing used. So we want to minimize the perimeter, which is x plus y plus x. The fencing of the field, it's just x plus y plus x, or 2x plus y. Now, once again, the idea is to get it down to a function of a single variable, but we have some additional information. We're told that the field has an area of 3,200 square yards. Okay, so A, which is xy, is 3,200 square yards, or y is 3,200 over x. By the way, I'm just solving for y in terms of x instead of x in terms of y. It could have been done either way. Okay, so letting y be 3,200 over x. P is 2x plus y, which is 3,200 over x. Now, what can we do about the interval here? Once again, closed interval is out of the question. In order to have an area of 3,200, x is greater than 0. It's between 0 and there's no upper limit here. It's between 0 and positive infinity. You have some, basically x is positive. Okay, it's greater than 0. 0 is less than x, less than infinity. X is some positive value. It has to be positive. Well, negative doesn't make any sense, and 0 is out of the question in order for the area to be 3,200. Now, same procedure. Get the derivative. Well, first let's write this over as 2x plus 3,200x to the minus 1 instead of the quotient rule. Then the derivative would be 2 minus 3,200x to the minus 2, or 2 minus 3,200 over x squared. The algebra is very similar to the work that we had in the preceding problem. We set it equal to 0. We get that 2 is equal to 3,200 over x squared. Cross multiplying, 2x squared is 3,200 dividing by 2. X squared is 1,600. X would be plus or minus the square root of 1,600, or plus or minus 40. Now, we had an interval from 0 to infinity, so x equals 40 is the only critical number on the interval in question. So if we could show that there is a local min when x equals 40, it would also have to be the absolute min. Let's make our chart, x against p prime here. Our critical number is 40. Let's try a value less than 40, 10, a value more than 40, let's say 60. Let's substitute into P prime. P prime is 2 minus 3,200 over x squared. Substituting x equals 10, 2 minus 3,200 over 100. 2 minus 32 is certainly negative. Substituting 60, 2 minus 3,200 over 3,600. 3,200 over 3,600 is certainly less than 1. 2 minus something less than 1 is certainly positive. The function was decreasing before the critical number, increasing after, giving us a local min at that point, plus the fact that there is only one turning point, guarantees that this is the absolute min. Now, what's the answer to the problem? What dimension should the field have? So we know that x equals 40 is the correct answer. Let's figure out what y is. X is 40, y is 3,200 over x, so 3,200 over 40, or 80. So the answer should be, x should be 40 yards, and y should be 80 yards. This will give us an area of 3,200 square yards. Notice for the first time on this tape, the answer was not a square. Okay, but if you think about it, it makes sense. You're not paying for fencing on the riverside, so obviously you'd want to have the side opposite the river longer. In fact, it really was like a square, 40 on each side, except we took the 40 feet of fencing we would have put here and we put it down here. So that's how come we wind up with the answer 40 yards by 80 yards. The longer side opposite the river, because we don't need the fencing on the riverside, so we take advantage of that. And that's how we minimize the fencing and still get a 3,200 square yard area. Okay, a rectangular field, this is problem 4. A rectangular field is to be fenced in and then subdivided into 3 plots by erecting fences, building fences parallel to one of the sides. What is the area of the largest field that can be fenced in with 600 feet of fencing? So we have our rectangle, what we've had before. All of the problems on this tape deal with rectangles. The next videotape, max-min problems, will be a variety, miscellaneous problems, but we're concentrating on rectangles here. We have a rectangular field, and we're going to subdivide it into 3 plots by erecting fences parallel to one of the sides. So let's say the dimensions are x for these fences and y for these. Now, we have 600 feet of fencing, that's all we have, and we want to get the field that has the largest area. So we're back to maximizing the area of the field. Now, I'm talking about not the plot, but the whole field, maximizing x, y. Now, we'd like to get it as a function of a single variable. And how do we do that? To get a single variable, we need to look at the additional information. We only have 600 feet of fencing. So all the fencing, we have fencing here, 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 here. That is 4x plus 2y has to add up to 600. We're going to use all the fencing because we want to have the largest possible field, but it's a variation on the perimeter that we had before. It's the total amount of fencing. 4x plus 2y should be 600. So 2y is 600 minus 4x, and dividing by 2, y is equal to 300 minus 2x. Well, if we know what y is, we can substitute that in here. A is equal to x times y, or x times 300 minus 2x. So we want to maximize A, which is 300x minus 2x squared. Now, what about our interval? This goes back to the first problem that we did on the word problems. You have a choice of an open interval or a closed interval. If you consider it to be a closed interval, then your restrictions are clearly that x has to be greater than or equal to 0. And how high can it go? Well, whatever x is, there are 4 of them. So even if y were 0, the 4 x's would go up to 600. If y was 0, the biggest x could be would be 150, if you're doing it that way. If you want the open interval, we'll do it that way in a moment. Okay, to do it as a continuous function on a closed interval, which you can do, you get the derivative, 300 minus 4x. We set it equal to 0. We get the critical number. 4x is 300, x is 75. 4 into 300 goes 75 times. Okay, now you would make yourself a chart, x against a. The endpoints of the interval are 0 and 150. The only critical number that we got, 75, does fit into this interval. We put it in here, and we figure out what a is in each case. If x is 0, a is 0. If x is 150, 300 minus 300 is 0, a is also 0. Those are the 2 trivial cases where x is 0 and use all the fencing on the horizontal sides, or if x is 150, you're using it up all on the vertical sides and nothing left for the horizontal sides. If, on the other hand, we have 75, the area will be 75 times 300 minus 2 times 75, 300 minus 150 times 150. Now, clearly, the biggest of these numbers is this one here, and that's the absolute maximum. So what is the area of the largest field that can be fenced in with 600 feet of fencing? That's 75 times 150. 75 times 150 turns out to be 11,250 square feet. Is the maximum area. And the dimensions, of course, x is 75, y is 150. So you have the 4 75-foot fences this way and the 2 150-foot fences that way. Now, let's say you really feel that this should be instead an open interval. Then your problem becomes one of maximizing a, which was 300x minus 2x squared. That was the original problem. On the interval 0 to 150, the open interval. In other words, for x strictly between 0 and 150. I am not going to allow x to be 0, but anything larger than that will be acceptable. And obviously, while I won't let x be 150 because that would use up everything and nothing for the horizontal fences, anything under, no matter how small, I could always divide it in half and use it for the 2 horizontal sides. Now, if you do it this way, you once again get the critical numbers by taking the derivative and setting it equal to 0, and there's only one critical number, x equals 75 on this interval. And you try to determine if this is a local max or a local min. You take a testing value less than 75, let's say 70, more than 75, let's say 80. You substitute into a prime. Plugging in 70 here, 4 times 70, 280, 300 minus 280 is positive. Substituting x equal to 80. 300 minus 4 times 80, 300 minus 320 is negative. The function was increasing and then decreasing after the critical number, giving us a local max. And there's only one turning point. Which implies that it is, in fact, the absolute max, which is what we were looking for. And of course, the answer remains as it was before, 75 times 150, or 11,250 square feet for the area. Okay, in this problem, the last one on this videotape, we have a rectangular field to be enclosed using two types of fencing. The two opposite sides that run north-south will require a heavier fencing, which sells for $3 a foot. The two sides that run east-west will use a lighter fence, which sells for $2 a foot. What are the dimensions of the rectangular field of greatest area that can be fenced in at a cost of $12,000? We have a limited amount of money that we can spend on fencing. So in a sense, a limited amount of fencing, and yet we need to enclose the greatest possible area that we can. Okay, so we have our rectangular field. Okay, the heavier fencing is going to be on the north, the sides that are running north-south. So let's make this a little darker. Here's my heavier fencing for north-south, and the lighter fencing on the east-west sides. Okay, so we have the heavier fencing running north and south. Those are the vertical fences that we have here. The horizontal sides are the lighter fencing. The dimensions are going to be X for the sides that are running east-west, and Y for the sides that are running north and south. Okay, now we want to maximize, want the greatest area. We want to maximize the area. Once again, the area is XY. The area of a rectangle is length times width. That's not going to change. It's a little bit harder to get the extra condition here, because it's not a straight perimeter problem. There's a cost factor involved. Instead of maximizing the area subject to a fixed perimeter, we're maximizing the area subject to a fixed cost. Now, how does it work? Total amount that we have to spend on fencing is $12,000. The heavier sides are going to run $3 per foot for the heavier sides. So instead of having the perimeter fixed to be $12,000, it's the cost that's fixed at $12,000. So to get the cost, it's going to be the length of the fence times the cost for that particular fence per foot. The length of the fence in feet times the cost per foot. Same thing here. So the cost of this side will be X feet of fencing times $2 a foot. Here it'll be X feet of fencing times $2 a foot. Here, Y feet of fencing times $3 a foot. Here, Y feet of fencing times $3 a foot. So you'll have 2X plus 2X plus 3Y plus 3Y. 2X plus 2X plus 3Y plus 3Y. That'll be the total cost of the fencing, $12,000. Once again, it's not the usual 2X plus 2Y. It's not the perimeter, because the fence costs more on these sides than it costs on these sides. So we have to weight the length of the fence by the cost for that type of fencing. So it's X feet times $2 a foot. X feet times $2 a foot. That's a 2X and a 2X dollars. And here, Y feet of fencing, each one at $3 a foot. So 3Y and 3Y. Or 4X plus 6Y is 12,000 is our extra condition. Now, if we want to solve for either X or Y, if we solve for Y, 6Y is 12,000 minus 4X, dividing by 6. Y would be 12,000 over 6 minus 4X over 6, or Y would be 2,000 minus 2/3 X. So we could substitute that in here and get that the maximum, we want to maximize the area, which is X times Y, X times 2,000 minus 2/3 X. Now we need an interval here. Once again, we have a choice between an open or a closed interval. Let's figure out the endpoints. Certainly, the smallest x could be would be 0. So x has to be greater than or equal to 0, and the question is, how big could it be? Well, if you used no fencing for the north-south sides, but use it all for the east-west, then the biggest that x could be, before x would be 12,000, x could be 3,000. Would be the biggest you could let it go. And the other choice would be, of course, the open interval, where you say, I will not accept an x of 0, nor an x of 3,000, which would have used up everything on one side. I want to have something on the other side. So we'll do it with the closed and with the open interval. So let's go over here. What do we have? We have maximize a equal to, just write it over, x times 2,000 minus 2/3 x on the interval from 0 to 3,000. So a is 2,000x minus 2/3 x squared, distributing the x through the parentheses. Just notice how this is just like the first problem we started the videotape on, to maximize a function subject to a restriction on the variable on a closed interval, a continuous function on a closed interval. The only trouble here, we had to spend a little time figuring out how to get the function, how to get the interval. If you're having trouble with the interval, once again, let me explain that I'm saying that x can't be negative, because it doesn't make any sense in the problem. And to figure out how big x can be, I take this equation, I said, well, the biggest x will be as if y was 0, in which case 4x would be 12,000, so I know the upper bound for the x would be 3,000. 4x is 12,000, x would be 3,000. Okay, taking the derivative to get the critical numbers, 2,000 minus 4/3 x, and setting it equal to 0. 4/3 x is equal to 2,000. X would be dividing both sides by 4/3 or multiplying by 3/4. Divide both sides by 4/3. Instead of dividing by 4/3, I invert and multiply by 3/4. 4 goes into 2,000 500 times. 500 times 3 is 1,500. And we're talking about feet. Okay, so x would be 1,500 feet. Let's see if this gives us a max or a min, whatever we have. Let's see. Continuous function on a closed interval. The endpoints are 0 and 3,000. And the critical number that we got was 1,500. Substituting into the original equation here, if x is 0, of course the area is 0. If x is 3,000, substituting in 3,000 here, 3,000 over 3 is 1,000. 2 times 1,000 is 2,000. 2,000 minus 2,000 is 0. So in either extreme we have that. The area is 0. And the other case, you have that the area is x is 1,500 times 2/3 of 1,500. Substituting in 1,500. 3 into 1,500 goes 500 times 2 is 1,000. 2,000 minus 1,000, so it's 1,000. So 1,500 times 1,000 for an answer of, they ask for the actual greatest area. They ask for the dimensions, but we have this, we may as well give it. 1,500 times 1,000, or 1,500,000 square feet. Those would be the dimensions. In other words, x would come out to be 1,500, and y, 2,000 minus 2/3 x, we figured out would be 1,000. So those are the dimensions, and the area 1,500,000 square feet. Now that's the way to do it for a continuous function on a closed interval. Or you could say I want to maximize a, which was 2,000x minus 2/3 x squared, but the interval is really the open interval 0 to 3,000. So then when you get your derivative, which is, as before, 2,000 minus 4/3 x, and you set it equal to 0, and you get 4/3 x is 2,000. We're inverting and multiplying, as we did before, by 3/4. We get 2,000 times 3/4, 1,500. We want to determine if we have a local min, and then if it's one turning point, we only have one turning point on this interval, it would be an absolute min. So here we make the chart like this, x against a prime. We take the 1,500, the only critical number that we got. We sandwich it in between any other values you want to use. Let's say we use 1,200 and 1,800, but you can use any numbers at all. I try to pick things that would be evenly divisible by 3 just to make my life easier. But I substitute now into a prime, not into a, but into a prime. Substituting 1,200, 3 goes into 1,200 4 times, 4 times 400, 1,600. 2,000 minus 1,600 is positive. Substituting in 1,800, 3 goes into 1,800 6 times, 4 times 600 times 4 times 600 is 2,400. 2,000 minus 2,400 is negative. The function was increasing prior to the critical number decreasing after, giving us a local max at this critical number, plus the information that there was only one turning point on the interval. Guarantees that the local max is in fact an absolute max. So that would be the other way of finishing up this problem. So we know the dimensions, 1,500 feet by 1,000 feet. And that brings us to the end of this problem and to the end of the videotape.